Hello, my name is Jeff Pryor, and today I'm going to be giving a short and brief introduction into the topic of aerodynamics. And the goal of our talk today is to, at the end, use methods of partial differential equations to solve and derive an equation for lift in a very general and ideal case. So let's get right into it. Before we talk about aerodynamics, we're going to start by talking about fluid mechanics because fluids are the basis for all aerodynamics. We're talking about movement within a fluid. And a fluid is any liquid or gas, and it's basically just any matter that takes the shape of its container. And then when we talk about fluid mechanics, there's two different distinctions that we can make. We can talk about fluid statics, which is fluids that are not moving at all, and fluid dynamics, which are the study of fluids which are moving. And you see we have fluid dynamics bolded here. There's going to be a couple terms that were bolded. Those are going to be the terms that we're kind of focusing on and making assumptions for in this presentation. What we're really looking at when we're talking about fluid mechanics is the study of fluids along the effect of a boundary of a body. If we think about a body moving within a fluid, the fluid is actually moving around that body. And so that's when we get movement of the fluid. And for today's case, we're going to talk about steady flow of fluids, which this means that conditions such as velocity will not change with time. So we're talking about fluids moving at a constant velocity. Before we get into it as well, we'll talk into a little bit about geometry and viscosity. These are two obstacles that we face when we talk about fluids because geometries and viscosities can make fluid problems very difficult to understand and mathematically to derive equations for and solve equations for. So when it comes to geometries, it's difficult to study arbitrary geometric shapes. It's easier to focus on much simpler shapes, and for today's case, we're going to focus on cylinders. And along with that, viscosity, it increases the difficulty of your basic equations because it adds different variables in, and it creates a destabilizing effect on all fluids that cause turbulence. So turbulences are generally small velocities, but they're disorderly and they're crude, and they're very hard to predict. It seems like more of a random phenomenon, so it makes it much more difficult to talk about fluids when we're considering different viscosities. And sometimes we're going to neglect it, and that's what we call an idealized flow. And for today, we will also talk about idealized flows.
So jumping right into talk of this lift force, we know we can induce this force through movement of a body. And we're going to make the assumption that
we have a cylindrical body of radius A. Again, we're talking about a cylinder, and we're going to have it moving in the positive x direction. And the force of lift is going to be in the positive y direction. And this lift force is actually going to be induced by pressure. We know for steady flows, Bernoulli's condition for pressure is that pressure plus 1/2 rho v squared is equal to some constant. And this means where the velocity is low, pressure must be high. And this means that if we can create lower velocity below our body, that means we will have higher pressure below the body, and thus the body will lift. And to the left, over here in the bottom left corner, we can see some different examples of flows around our cylinder.
Now these here are very basic cases where C1 is actually the viscosity of the fluid, so it's a characteristic of whatever fluid we're discussing. And our cylinder again is moving in the positive x direction, which here is to the right. We will introduce later that capital U is actually the speed of our cylinder, and therefore it is also the speed of our fluid.
So now we're going to use this streamline, or a stream function, to derive our equation for lift. Again, we're talking about methods for solving partial differential equations here. So we're going to assume that our stream function psi is graphed parallel to fluid flow, and psi is going to be equal to some constant. We're talking constant fluid flow again. So the fluid is irrotational, and so that means that it must satisfy Laplace's equation. And our fluid being irrotational is just another idealized assumption we're going to make for the case of our talk today, and this means that the del squared operator multiplied by psi is going to equal 0. And then we must take into account conservation of mass. For any fluid, obviously, this is a physics concept that we cannot destroy or create any mass. That's just a general concept of physics. And our velocity vector we'll call u of the fluid has x and y components, and we'll call those u and v respectively. The constant fluid density with respect to time is where we get our steady flow. Again, this fluid density is going to not change with time. So in 2 dimensions, we must satisfy the equation del dotted with u is equal to 0, or the partial of u with respect to x plus the partial of v with respect to y is equal to 0. So we're going to introduce our stream function such that that equation for the conservation of mass, the partial with respect of u with respect to x, plus the partial of v with respect to y is equal to 0. So that means that our u, or x component of our velocity vector, is equal to the partial of psi with respect to y, and v is equal to the negative partial of psi with respect to x. And again, we're assuming our body is moving at constant velocity in the x direction, so the fluid is moving such as some constant velocity. I'm going to call this capital U, because we're talking the u component, the x direction, and obviously it's not moving in the y direction, so that will be 0. And therefore, you can see capital U is going to be equal to the u component, the x component, which is the partial of psi with respect to y. And if we do a little separation of variables here and take an integral with respect to y, we see that psi must equal to u y.
Now we're going to move into polar coordinates here because again we are discussing a cylinder, so this will greatly simplify things in the end. And so when it comes to uy, we know this is also equal to ur sine of theta in polar coordinates. And again, we're talking very generally, so this condition of psi must be satisfied even if we have a large r.
And now for our partial differential equation, we must set up a boundary condition. At the boundary of our cylinder, r must equal a. Again, we're talking about a cylinder with radius a. So the fluid must be parallel. The fluid must be flowing right around our boundary, our cylindrical boundary. And at that point, it has to be parallel to the boundary. The fluid going around has to be parallel right at that boundary.
And theta actually is a reference angle between the boundary of our body and the fluid, so if the two are parallel, it must mean that the angle, or theta, is 0. This means that psi, evaluated at radius a, the boundary of our body, must equal 0.
And as we set up our partial differential equation, we know intuitively that because we're in polar coordinates, that our streamline function is only going to depend on r and theta. Therefore, we can say that our streamline function psi is some product of a function phi in terms of theta multiplied by some function g in terms of r.
And we know the first partial with respect to r of psi is g prime of theta, or g prime of phi, excuse me, and the second partial with respect to theta of our function psi is going to be equal to g phi double prime. And now we know the partial differential equation for polar coordinates is 1 over r partial of r phi partial r with respect to r plus 1 over r squared multiplied by the second partial of psi with respect to theta, and that's going to equal 0. And that all comes from a different background in partial differential equations. We don't exactly have time to get into how we derive that necessarily at this time, but if you find some general background in partial differential equations, that is a very common concept there. And if we divide by 1 over r squared g phi, we will get rg prime plus r squared g double prime over g is equal to negative phi double prime divided by phi. And in order for these to be equal, if we have a function of g equaling some function of phi, we know that in order for these to be equal, they have to equal some constant, and we're going to call this constant lambda. And if we go through the method for solving our partial differential equation, for our phi equation, we'll actually find that lambda n is equal to n squared. Again, we don't have time to necessarily go into that. That's a very general solution for a partial differential equation. Actually, this is a very general solution for an ODE if we're just talking about the phi portion. And lambda equals 0 is a non-trivial eigenvalue, so it must be that the integer n equaling 0 must be considered. And the reason we index by n is because we know our solution to this PDE is going to be some summation. So the general solution actually is psi of r theta is equal to c2 plus c1 natural log of r plus the summation from n equals 1 to infinity of an r to the n plus bn r to the negative n, and that whole quantity multiplied by the sine of n theta. And we know the sine n theta portion comes from that there's a general sine n theta plus cosine n theta that we would have gotten from the phi equation. That would have been our solution to that equation. But the cosine n theta is actually going to go away, and so that's where we get just the sine n theta, and then the portion in parentheses there, the an r to the n plus bn r to the negative n, comes from a solution to the g formula. And then the c2 plus c1 ln of r out front there actually comes from the fact that n equaling 0 is a possibility for this case, because we said that the eigenvalue lambda equals 0 is non-trivial. And so if we apply the boundary condition at r equals a for the g of r solutions, that is the part out in front, the c2 plus c1 ln of r, and the sine of n theta portion, we see that 0 equals c2 plus c1 ln of a, when n equals 0, and therefore C2 must equal negative C1 natural log of A. And if we say that 0 is also equal to an little a to the n plus bn little a to the negative n, because again we're plugging in a being our boundary condition, the radius, and we know that equals 0. When n does not equal 0, we get that b little n, or b sub n, must equal a sub n little a to the 2n. Thus our solution becomes as follows there. If we do a little substitution and some manipulation, we can get there.
However, our function psi describes the movement of our fluid, and in order for the fluid velocity to be constant, as we set up before, we know that we can't have an infinite series as we have described by our finite sum. If this were the case, the velocity of our fluid would blow up towards infinity. Therefore, all ANs, where n is greater than or equal to 2, must be equal to 0.
Also, in order for that condition that we set up before, that psi equals ur sine theta, when r is large, it must be that a1 has to equal u. That's the only way this is going to work. And that will leave us with this equation here. And that is basically, we've gotten rid of the summation now because we know that the ANs are all equal to 0 for all n greater than or equal to 2, so we don't have to worry about the summation anymore. And if we're looking for velocity of a circulating fluid around a cylinder, in polar coordinates, we know a circulating velocity, fluid velocity, is the partial of u with respect to theta, and that equals the negative partial of psi with respect to r. And if we take that partial of the u vector, we see that that's equal to negative c1 divided by r minus big U, quantity 1 plus a squared over r squared multiplied by sine theta. And according to the laws of physics, we know that force related to pressure, force is pressure multiplied by the cross-sectional area of the body with respect to that force, and therefore our force in the y direction, again we're talking about this lift being in the positive y direction, is equal to negative the integral from 0 to 2 pi of pressure times a being the radius of our cylinder times sine theta d theta. And revisiting Bernoulli's condition, we see that P is equal to negative 1/2 rho v squared. We talked about that before, Bernoulli's condition. And so we can plug in or substitute this P, this value of P, the negative 1/2 rho v squared, into our equation above for a lift in the positive y direction. And therefore, we see that the lift force, if we take this integral from 0 to 2 pi, using our equation that we just derived before about our fluid moving around our cylinder, rotating around our cylinder, and we can finally find that when we take this integral, that the lift force is generally this force in the positive y direction equaling 2 pi c1 rho u. And again, we talk about u being that velocity in the positive x direction, and c1, again, as we discussed before, is a property of our fluid. And that is a very general formula. That's what we wanted to derive today using our methods for solving partial differential equations. If you want, you can go look to other resources for solving partial differential equations if maybe you got lost in that portion of the presentation. But that, in general, is a equation there for the lift of a cylindrical body moving through a fluid at constant velocity. And if you have any questions, you can feel free to email me. Again, my name is Jeff Pryor, and my email is shown below as jeffreypryor12@augustana.edu. Thank you.